Hi, hello everyone. This is your Ragvi Deva. Today we are going to see the topic is about MOS logic family. So in early videos, we saw about the introduction part of MOS transistor. Here we have the classification as first one is NMOS logic family, it to be built with N channel, and second one is PMOS logic family, it to be built with P channel, and third type is CMOS logic family, it to be built with P channel and N channel. Right. So we see the first part of NMOS transistor. Obviously, as I told early, it has two types of operating mode. One is depletion mode and one is enhancement mode. If we work with depletion mode, uh, it to be reverse condition of enhancement. Enhancement mode is it's behave like normally switching conditions. If you provide the supply, it will be on mode. If you not provide the supply, it will be in off state. But depletion mode is exactly opposite to that enhancement. If you provide the supply, it will be in off mode. If you not provide the supply, it will be in the on conditions. Here you see the gate terminal, input terminal, we not provide any supply, which represents the gate equal to 0. Right. So in these conditions, the transistor get on. If you provide the in enhancement mode, you see if you provide the supply, the gate terminal equal to 1, which means enabling conditions, the transistor get on. So these are the basic difference between the depletion and enhancement mode. In depletion mode, the transistor should be connected between VDD and the output. Enhancement mode, it should be connected between the VSS and output. These are the symbol representation we shown here. So what is the basic difference between this symbol representation means? So in depletion mode, we do a shade in the terminals. Enhancement, we never do that shade conditions. So these are the basic difference between the enhancement and depletion mode. So under CMOS, we'll see how the depletion mode transistor get represent and enhancement mode transistor get represent here. So basically NMOS, the current conductions is because mainly of the electrons, and one more point of electrons is about the negative charge electrons is moving faster than that of the holes. So the speed of the operation of NMOS is much faster than that of the PMOS. So here they taken the design of inverters, basic logic gates, how we can implement it in that NMOS logic, PMOS logic and CMOS logic transistor. So this is the basic symbol representations and basic truth table here they represented. So inverter input condition as A, output as A bar. If you provide the input as 0 to the inverter terminal, it provides the output as 1. If you provide input as 1, it provides the output as 0. This is the basic inverter logic, right? So this logic we are going to implement it in the NMOS logic family. There we are using two modes of transistor. One is depletion mode and one is enhancement mode. So here you see this is the inverter representation of NMOS logic family. So consider the NMOS transistor. Uh, this is the lower part of transistor as NMOS enhancement mode transistor. Upper part of transistor, which is the NMOS depletion transistor. So here you have gate terminal, drain terminal, source terminal of T1 transistor, that is enhancement mode transistor, and T2 transistor also you have gate terminal, drain terminal and source terminal, right? Okay, so in this you see uh, depletion mode act as a load, enhancement mode act as a driver. So which represents it will be always in a on state conditions. Depletion mode, we need not to provide any supply, it will be always in a on state conditions, which means the gate is feedback to that drain regions, right? So it will be always connected as a feedback terminals. We never need not to provide any supply. Here it represents the gate voltage is 1, right? Okay, so VDD conditions, the VDD passes over this transistor, it will feedback to that through the gate terminal, so it will be always in a operating mode of 1. And then So this is the driver transistor. Depending upon the input condition, it to be react, and based on that we can get the output. If suppose initially we are providing the supply as 0, right? So NMOS transistor, when it gets enable means, if you provide 1 it will be enable, if you provide 0 it will be not enable. Like if PMOS means, if you provide 0 means, because PMOS we are using bubble, right? So bubble meaning is that it will be do the inversion conditions. So PMOS transistor, if you want to on the PMOS transistor, if we provide the supply 0, it get inverted 1, and that 1 will get passed on to the transistor, it will be enable the transistor. If we provide 1 means it get inverted, that 0 will be passes to the transistor, which represents it will be in a off mode. So what conditions we are taking, what logic we are taking for NMOS, the reverse logic we have to consider for PMOS. If you want to enable the NMOS transistor, if you want to on the NMOS transistor, we have to provide the logic 1. So in these conditions we have for inverter design we have two logic. One is we have to provide input 0, and one more condition is we have to provide the input 1. We check the conditions whether this design has to support that inverter logic. If I just provide the input voltage as 0, the bottom part of T1 transistor not on condition, in the situations this VDD it will be on, the upper part of transistor always on, that VDD get passed on to the output, right? 1 0 conditions, output as 1. If I provide the supply 1 for gate terminal, this T1 transistor enable, that ground 0 value will be passes from below to that output terminal. So in a situation if you provide the 1, the output is 0. So this is basic, it satisfy my inverter operations. So this is the way we are designing the NMOS logic. So earlier days, instead of this depletion mode transistor, they use it act as a load. Depletion mode, it will be act as a load conditions. So earlier days we are using, instead of that transistor we are using the resistor element. So depletion conditions, the depletion transistor earlier days it will be used by the resistor, one of the passive components, but later it will be replaced by the transistor active component. Why? Because means so to fabricating a resistor is very difficult in this logic by using silicon material, because it requires more amount of silicon comparatively the active component of transistor. The passive one require more amount of silicons. So due to that drawback, they move on to design the load terminal as by using the active component in the depletion mode conditions. So these are the reasons they are given why you want to resistor to passive element to active component. So earlier days we are using resistor element between VDD and output in depletion conditions, and ground to output is an enhancement condition, that is VSS to output, that is the enhancement transistor. But because of this drawbacks, later they move on to active element transistor between VDD to output as a T2 transistor, depletion mode transistor. In order to differentiate the enhancement mode transistor, depletion mode transistor, they provide the shade over the transistor. And between output and ground, that is between output and VSS, we have the active type of transistor. Under our logic, we are going to implement using enhancement mode transistor, because enhancement work under provide the supply on conditions, not provide the supply during the off conditions. It will be act according to our instructions. So we try to prefer that driver mode conditions. Whenever the driver mode conditions is not providing the output, in a situation the depletion mode uh, provide the output value. All right, so this is the examples we see for inverter conditions, and few more examples we can see for NMOS logic conditions. You are just considering the AND gate logic as multiplications A dot to B. So this is the symbol represents we are giving for AND logic. Here, early days we consider only one input, A as alone, providing the output as A bar. But AND gate logic, we are going to provide two input. Into input logic conditions, how we are going to design using NMOS, right? So here, mm, excuse me, here and logic we have to use a dot operation, that is multiplications operations, right? So rule 1, you see, if we are using dot operations, which means A dot B, B dot A dot C. So likewise, multiplications operations we are using means that NMOS enhancement transistor should be connected in series form. Again, I telling you, if you are using the dot operation conditions, this is only for enhancement, NMOS enhancement transistor to be connected in a series form. And rule 2 as, if you are using the operation as plus operation, that is A plus B, B plus A, C plus A. Likewise, addition operations we are using means, plus operation means NMOS enhancement transistor to be connected in a parallel form. This is the logic we are going to use it for designing the AND gate model, right? So these are the truth table we are given here for AND gate. So what is the combination of AND gate? Two input AND gate, 0 0 0 1 1 0 1 1. These are the combinations, because two input means 2 power n, which is equal to 2 power 2, equal to 4 possible combination. That 4 possible combinations we are design A B 0 0 0 1 1 0 1 1. Output for AND logic, whenever you have to enable input, that is A equal to 1, B is equal to 1, our output is 1. Otherwise, remaining cases our output is 0. So these are the truth table here. With that truth table conditions, whether it to be satisfied or not using NMOS logic, we are going to check and we are going to design for that model. So here you see, this is the AND gate using NMOS logic implementations. So in this logic, you consider the first part T1, T2, T3 implementation. This is AND gate. That AND gate implemented using NMOS with the help of inverter base. So inverter model of design, we are using upper part as depletion mode, lower part as enhancement mode. So the same method also we are going to follow here. So upper part as depletion, lower part as enhancement. Upper part in technically we call it as a pull up network, lower part technically we call it as a pull down network. Okay, fine. Okay, so in this upper part, always we are considering only one depletion transistor. It is always feedback to the drain region. Okay, so depletion transistor which is connected between VDD and output, enhancement transistor is connected between VSS and output region. And one more point I add on here, here AND logic A dot B dot operation means NMOS enhancement to be connected in series. So here NMOS region as T2 and T3, because A as one input, B as one input. So it to be connected in a series, because A dot B, so it to be connected in a series form, right? So this is the way I connected this transistor. And here we are using the logic of inverter, right? Upper part depletion, lower part enhancement. If you want to get the original output means, in this AND logic we are going to connect the inverter design. If suppose NAND logic means the same architecture, this is AND gate using NMOS. For NAND gate, so the same structure of AND without inverter model of design, right?